Section 8.1 talks about something called L'Hopital's rule. This deals with limits, so we're going way back to the beginning of the school year and the beginning of calculus. And this is a rule that will give us a easy way to calculate those limits where when we plugged in the numbers we got these indeterminate forms where we got 0 over 0 or infinity over infinity, and we couldn't actually calculate the limit by plugging things in. So this is going to help us with that. The first form of L'Hopital's rule, which actually is very simplified and it isn't exactly how we're going to use it, but it gives us an introduction, says suppose that f of a equals g of a equals 0, and that f prime at a and g prime at a exist, and that g prime of a is not equal to 0. Then if you have the limit as x goes to a, which we would plug it in and end up getting 0 over 0, then that's equal to the derivative at both of those points. So let's see how we got that. Well, you'll remember that the definition of a derivative, or one of the definitions we looked at for a derivative, says the limit as x goes to a of f of x minus f of a over x minus a equals the derivative at this point a. This was from the very beginning of the school year when we were first talking about derivatives. So if we use this, we can actually look at this and we can put in g also, and same definition of a derivative here. Then if we use this and put it all together, then we know that the derivative of f divided by the derivative of g at this point a is equal to the limit as x goes to a of f of x minus f at a all over x minus a over the limit as x goes to a of g of x minus g of a all over x minus a. And so we can calculate this out and see that since this is 0 and this is 0, and if we separate this, remember when you're dividing it you can take the limit individually, and so we'll end up with all these fractions, and this will cancel with this, and we'll get the limit as x goes to a of f of x divided by the limit as x goes to a of g of x, which we can put all together as one limit, which is the one we were originally looking for. Make sure you remember how to simplify that all down and split that all up. But that's L'Hopital's rule. Now, as I said, that's a pretty basic form of it, but let me give you an example here. If we have the limit as x goes to 1 of x cubed minus 5x squared plus 6x minus 2 over x to the 5th minus 4x to the 4th plus 7x squared minus 9x plus 5. And we wanted to figure out what this limit was. If we plugged it in, plus plugged in 1, we'd get 0 over 0. And we know that most of the time what we try to do is factor and simplify it down, take those removable discontinuities out so that we could then plug it in. But these are pretty big polynomials. It would take you a while to factor this. So what you can actually do is use L'Hopital's rule because we got 0 over 0, and we could use the derivative at this point x equals 1. So what we would have is take the derivative and plug in 1, and I'm sure you know how to calculate derivatives by now. And this is what we get. And when you calculate that all down, you get 1/6. And so that was a very simple way to deal with it because we knew L'Hopital's rule. Now, there's actually a stronger form of L'Hopital's rule that helps us for both the 0 over 0 and the infinity over infinity part. So let's look at that one. Again, we're going to suppose, this is in your book, so I'm not going to write it all the way out, but again, suppose that you have f of a and g of a are equal to 0 or to going to infinity, and that f and g are both differentiable on this open interval I, which contains a, and the g prime is not equal to 0 on this interval. Then we can say that the limit as x goes to a of f of x over g of x equals the limit as x goes to a of f prime over g prime. Now, how is that helpful? Well, that's really helpful because we can look at this and see that sometimes we're not going to get an exact value of the derivative at that point. It's sometimes not calculable, but we can calculate the limit. So then this gives us a stronger form so that we will be able to look at this and find the limit. For example, if we have the limit as x goes to infinity of e to the x over x, well, that gives us infinity over infinity. So we can use L'Hopital's rule and see that if we take the limit as x goes to infinity of the derivative of e to the x is just itself, and the derivative of x is 1, and then we can see that this is in fact going to infinity because we've simplified it down not to an indeterminate form anymore, but into something where we can actually see that the limit is going to infinity. Now, for those indeterminate forms where we have the powers, the ones we listed on the first screen where we had 1 to the infinity or 0 to the 0, things like that, we have a little trick where we can make it so we can use L'Hopital's rule. These are called power indeterminate forms. And what we're going to do is we're going to use this information right here. If we take the limit of the natural log of the function, and we can actually get a value for that, then we know that the limit of the function itself is equal to the limit as x goes to a of e to the natural log of f of x, which is e to the L. So whatever we get here, it's going to be able to plug in here. Now, hopefully you recognize that this and this are the same thing because e to the natural log of something is just whatever that something is. But this helps us so that we can find this limit here. Now, how does that help? Well, let's try an example. If we have the limit as x goes to infinity of 1 plus 1 over x to the x power, if we try to plug in, we're going to get infinity to the infinity power. Or, yeah, we're going to get an infinity power, 1 to the infinity power. Sorry, 1 to the infinity power. And that's not going to help us. We can't really calculate that out. So what we need to do is look at the log, the natural log of this function. So if we take the natural log of this function, we know with our log rules we can pull the x out front. And this still actually doesn't help us because it gives us an infinity times 0, which when we take the limit, which isn't going to help. So what we're going to do is we're going to just rewrite it a little bit. We know that multiplying times x is the same thing as dividing by 1 over x. So this, if we take the limit as x goes to infinity of that, we end up with 0 over 0, which is an indeterminate form, which means we can use L'Hopital's rule. So we use L'Hopital's rule to calculate this limit, and we get the derivative of that is 1 over 1 plus 1 over x times, don't forget to do the derivative of what's inside, all over, and then take the derivative of the bottom part, because remember, we're taking the derivatives individually, not the derivative of the whole thing, but the derivative of the top part, and then the derivative of the bottom part. And we'll actually look at exercise to show why that works in class. But you take the derivative of the individual pieces, not the whole thing. So we're not doing all the bottom times the derivative of the top and all that stuff. Just take the derivative of the top and then take the derivative of the bottom. That's L'Hopital's rule. So when we simplify this down, we get the limit as x goes to infinity of 1 over 1 plus 1 over x, which is 1. And that means, how does that help us with this one? Well, we can use this rule up here at the top. So this is the same thing as the limit as x goes to infinity of e to the natural log of 1 plus 1 over x to the x power, which equals e to whatever we get for this limit here. So it's just e. So then we can calculate this limit out using this information here. And then here we use L'Hopital's rule to calculate that limit out. So this is a lot of stuff to remember. Make sure you've read through this section and put the L'Hopital's rule and this little trick here with the other power indeterminate forms on your cards for where you're studying. One thing you need to remember is with L'Hopital's rule, you can actually use it multiple times if you have to take the derivative multiple times to get to a form that you can actually work with, because if the limit of the function divided by the function equals the limit of its derivative divided by the other function's derivative, then you can just keep going, because then you have a function and its derivative and its derivative and its derivative, and keep going. So that will give you multiple resources. Make sure you've read this section, written down your questions, and we'll go over several things more about this in class.